So hello everyone, welcome to the mind map of this particular chapter. Actually, this is for two chapters actually, for solids as well as liquids. Um, for solids, we will be mostly looking at the deformity perspective, but in the liquids, we will be mostly looking at the mostly in the of dynamics of the liquids. So first of all, in the solids, what we have is first of all, if you have any solid, let's say if you have a solid, if you compress it from both sides, of course that will lead to the intermolecular forces between the particles getting distorted, because of which they will get more closer to each other as compared to what they were previously. So all this compression, if you are compressing in this side from that side as well, then compression will be along this length, right? So this length will actually get reduced. What we define that reduction is, it is in the form of strain. Let's say this was initially L, and after compression this has become something of a L dash. All right, then strain is defined as whatever the reduction is in the dimension. I'm calling this as dimension because we will have different types of deformities as well. This we are looking from only one of the dimensions, but later we will have volumetric compression as well. So I'm calling this as a general term. Strain is equal to delta L divided by L. Delta L means reduction in length divided by the original length. Now, the reduction has been in the same direction as the force. That is why we give it a name called longitudinal stress. Longitudinal stress. Sorry, strain. We'll talk about strain as well. In the same manner, we will have something called volumetric strain. What will that be? Imagine if there is this bubble of air, it is in the atmosphere, then some atmospheric pressure is acting on it. Let's say you take the bubble and maybe exert more atmospheric pressure, or increase the atmospheric pressure to be more precise. Then what will happen is, due to, you must have learnt about the ideal gas theory, that as pressure increases volume decreases. Of course this is not ideal, but still the relation between volume and pressure remains the same, that when one increases the other decreases. So if you increase the pressure, what will happen is the volume will look something like this. The volume will look something like this. Now what happened is, there is again some reduction in the volume. This particular volume, will be the delta V, the change in volume. So the volumetric strain will be defined as in the same manner. And there is this another type of strain which is called shear strain. It may be called as a unique one because in this case there is no particular dimensional compression here, but what happens is, let's say there's this block and it has been fixed from the ground, and what you do is exert some force on it. What will it will look like after some time is probably, I just made it more than, yes, it might look something like this, that the whole object has been, under the application of force, has been tilted. So this type of now how will we able to measure this type of strain? it is very difficult, right? Because there is no change in length. The length is still the same as the previous one. The volume is still the same. So the way we look into it is because what is visible in front of our eyes is the more the strain, the more will be the angle which it has been maybe bended. So shear strain itself is defined in the same manner, that is it is the angle through which it has been bent. All right. So these are the three strains on different types of bodies. In the same manner, let me use another color for you to, yes, there is something called stress. All right. Now, what is stress? How do we have strain? First of all, in the layman terms, we have strain because of some stress acting on us, right? When we say we are strained, we usually refer that there has been some, we have been under some stress. That is because we have strain. So stress is the cause and strain is the result of it. So in this longitudinal stress, longitudinal strain, what was the reason why this all strain happened? It was because of these forces, right? These forces. But the more these forces, it will not exactly be the same as, let's say, there are two bodies, this one and this one. The net force on this side as well as that side on will be is F, and in on this object itself the force F is acting on it. But since it has a less surface area, the force does not get distributed overly to the all of the or the more of area. That is why it it tends to have a more degree of strain. So in this case, what we see here is the stress is not exactly the force, it is force divided by area, right? So longitudinal stress is equal to force divided by area. In the same manner, what is the reason why this air was compressed? It was because of force due to the excess amount of air. But it actually results into something what we are already very familiar with. When you divide force with area, in case of fluids, it results into something called pressure. So it is nothing but volumetric stress is equal to pressure is equal to F by A, nothing else. In this case, it will again be F by A. But which side should we choose? Should we try? Let me make this diagram more 3D like so that you are able to visualize. Yes. Now, which side is the one with which we are going to divide this? Of course, it will be the side which is perpendicular to the force. Only on that face itself, the whole force is getting distributed, right? So we will take this area. Yes, shear stress is equal to force by area perpendicular. All right. Area perpendicular means perpendicular to the force. So these were the three: stress and strain. Stress and strain. Now, I will define something or I will state something. So there was this scientist with the name Hooke who gave a law that for each type of strain to be resulted, or for each type of strain, there must be directly proportional amount of stress which must be there. It means for any system, whether it is shear, whether it is volumetric, or whether it is longitudinal, stress is directly proportional to strain. The more the stress you provide to the system, the more the deformity will happen. And when you convert this proportionality into equality, stress is equal to K into strain. Now, this K, as we said, that we have three different type of strain and three different type of stress. The the equation linking both of them for each of the three cases should also be three different ones, right? So what I'll do is, and the three proportionality constant should also be different for each of them, right? So in this case, the longitudinal stress is equal to some constant which is called Young's modulus into longitudinal strain. In the same manner, volumetric metric stress is equal to the constant which is bulk modulus here into volumetric strain, and the shear stress is equal to some constant which is actually called shear shear modulus into shear strain. Now there is this one term which is very rarely used, that 1 by bulk modulus is called compressibility. You might keep it in mind. Okay, so these were the three equations which will associate stress and strain of each of the three types. I think with this explanation, this part has been clear, as well as this part, and Hooke's law as well. Modulus of elasticity, I think we can take it up here itself. Modulus of, first of all, Young's modulus, I think I already explained it to you what it actually was, that if you have the shear stress which is F by A, I think I should make it more, yes, F by A is equal to, what's the constant that will be there? Since we are talking about the longitudinal stress, we must have something called Young's modulus into the longitudinal strain, which is delta L by L. Isn't it the same equation that we are talking about? Of course. And if you want to find out the the Young's modulus here, it will simply be F by A L by delta L. Wait. Did I L? Yes, I think so. So longitudinal stress and strain. Yeah. Now in this case, the what's the, first of all, the pressure, right? What relates with the um, uh, volumetric strain and volumetric stress is the bulk modulus. So what is volumetric stress? It is nothing but the pressure itself, and should be equal to B into delta V by V. So B here becomes P by delta V by V, which is nothing but this term. And I also talked about the compressibility, so this part also must be clear. In the third equation which we had here, see this one, I can directly apply it here. um, the shear stress, which is nothing but the force by area perpendicular, is equal to the shear modulus. Yes, it is also called rigidity. Shear modulus into the shear strain, right, which is nothing but the theta itself. So in this case, if we calculate eta, it will nothing be F by A theta, which is this term. So I hope this was clear. Even if you don't remember the equations of each of them, if you just remember the Hooke's law for each of the three individual types of stress and strain, you will be able to get to here. It will not be a problem. So I guess this is clear now. Stress, I think we didn't exactly define stress, right? We did define strain, which was the change in the configuration or change in the uh, or the deformity, the degree of deformity divided by the original configuration of the body. But stress actually is, what I said was, if you have a block and you're applying some force on both sides, the way I defined stress was F by A. But it is actually the restoring force. What do you mean by restoring force? Let's say when I apply some force on both sides and it gets something like this. On the molecular level, if these were the two atoms, when you apply some force on both sides, they will eventually come almost or more closer to each other, right? But the more closer they are to each other, the more repulsive the forces are, right? Because of huge electronic repulsions. Both of the atoms have electrons on their periphery and electrons on their periphery, which actually come closer to each other, due to which they repel each other highly. Due to which they also exert the same amount of force, and only when our force is exactly countering this force, this system will be called an in equilibrium, right? In equilibrium, it is not like that the restoring force is not there. It is just that our force is exactly equal to restoring force. That is why the system remains as such. But the restoring force is the one which is opposing the compression. So stress is actually defined in the terms of restoring force. So restoring force per unit area. Of course, the numerical value of restoring force is the same as the force that we applied. But to be more precise, it is the restoring force in the stress. Okay. Now, I think this is clear, as well as this one. Now, talking about the energy which is stored in the in anything. How do we define the energy stored? Energy stored should be equal to the work done on the system. It should be equal to the work done on the system, right? When you are compressing this solid particle or solid mass from both sides, you must be doing some work to do so. But the same work that you're applying into the system while compressing it is the energy which is getting stored in that. And the moment you release all that force, you no longer apply the force, then the energy will be released as all of a sudden. So this will be work done while putting stress. Putting stress. So it should be equal to F dot dr, where the change in displacement is equal to 0 to delta L, right? When you do all of this, you will be left with half into the constant K into strain square. And this is nothing but energy stored into the volume of the object itself. Now, what is K? K is the modulus for each of the cases longitudinal stress, it will become Young's modulus. If you have volumetric stress, it will become bulk modulus. If you have shear stress, it will become the shear modulus or modulus of rigidity. For example, if you are talking about, let me just yes, if you are talking about, this is the energy stored in the object which is under the stress. And if you want to write it in form of independent of volume, you can just say energy per unit volume. Energy per unit volume. In many textbooks, it is written in this form. It is nothing but half into K into strain square. In case of longitudinal strain, energy stored in maybe elongated wire or rubber band, maybe half into Young modulus into delta L by L the whole square. In the same manner, you can replace the this one different type of modulus with the three types of modulus, and in the same case it will be the same strain. For example, if I write the second equation, energy stored in maybe compressed bubble, it will be nothing but half into bulk modulus into delta V by V whole square. Just a second. Yes, whole square. And this is the first equation, this is the second equation that you have to remember, but they are all more or less the same. In the third case, it will be energy stored per volume in maybe bent bodies, right? This is the case I'm talking about. Will be equal to half into the modulus of rigidity into theta square. As simple as that. So these three equations are very similar to each other, not very difficult to remember. So this was it for this part. And this is something called Poisson's ratio. I'll talk about it. See, when you compress a body or maybe elongate a body, whatever you in both the cases, let's say I'm elongating this body, I'm pulling this one and elongating it. It is a short example of longitudinal stress, right? But in real life, it never happens that it has become something like this, and it's very easy that the dimension has not changed. It is a perfect cylinder even now, but it's not like what happens in the real life. It actually results into something of this sort, in which the middle part is actually more elongated than the sides or the terminals. So what we have here is, if we call this one L, then this one L dash, the change between them, delta L, is equal to L minus L dash. The change in the, or the reduction in the width of the cylinder is called as, it was longitudinal, right? So it will be lateral strain, and there must be some force acting inside the system, right? In the middle, which is called as lateral stress. It is very easy to calculate the longitudinal stress, right? Because we have the area constant and the force we can easily calculate. but this type of internal forces are very difficult to calculate. They can only be estimated. So we estimate it as per the Poisson's rule, that the ratio of Poisson's ratio. It defines something called Poisson's ratio, which is nothing but lateral stress divided by longitudinal stress. This is Poisson's ratio, and with the help of, if you have the Poisson's ratio and if you know the longitudinal stress, which is very easy to calculate, you can estimate the more difficult part, which is lateral stress. All right. So this was about the Poisson's ratio. Yes, this is about the Poisson's ratio, and it is denoted with the term sigma. Sigma. The value of the Poisson's ratio, of course, cannot be greater than 1, but in real life, it actually varies between 0 to 0.5. So this was it, and this part of the mind map is something of more simplification. So what you do is maybe remember on your own, because this is there is nothing to be explained here. You just have to remember it. It's not so important to be more precise, but still, if you have that in mind, it will help. So I think this was it about the properties of solid, and to be more precise, the deformity perspective of the solids. We will move into the fluids now, liquids. This is the more interesting or more important chapter from the perspective of your JEE or NEET. Now, coming to, first of all, in this case, what we'll do is define pressure itself. For example, let's say you have your palm, and on your palm there is this 1 kg block. You can easily hold it if the block is wide enough. But let's say there is this same hand of yours, and on that there is this pin which has been placed like this, a pin. On top of it, there is this 1 kg mass. The pin may be assumed as massless or very low mass. Isn't it that you are holding the same mass on both of the examples? But still, this is going to be more painful. Why? Because the whole weight of 10 Newton of the box or the block, which was getting distributed evenly on your hand, is now distributed over only this surface area, while it was getting distributed over the whole surface area previously. So that is why we define something called pressure, because the force itself was not enough to calculate or to estimate many things in our real life. So we have something called pressure. It is nothing but force being applied divided by the area on which the force is getting distributed. Okay, so this is called pressure. And of course, this is delta F by delta A, pressure. And if you go into more and more smaller areas, this will become something like limit delta A tends to 0, delta F by delta A, it will become dF by dA. Has become the pressure. Okay, now if we have already defined the pressure, what we will go into is pressure inside fluids. We already know that the atmospheric pressure is more or less constant on the surface of Earth. So on any part of the surface or the surface of Earth, you have the atmospheric pressure more or less the same. Of course, it varies with the altitude, but on the sea level, it is almost the same. But pressure inside fluids do vary. Why? Let's say you have this flask full of water. The pressure on this point must be equal to atmospheric pressure, right? But let's say you talk about the pressure on the depth, it will be actually be holding up pressure of the atmospheric pressure plus pressure due to weight of the water, right? Weight of the whole water getting distributed over this area. When you simplify it, the pressure actually becomes something like P naught plus rho GH. You can quickly, if you're not aware of it, you can quickly derive this equation from what I said here, that the pressure will be actually the same pressure which is getting applied by the atmosphere as well as the whole weight of the cylindrical water container getting distributed over the basement. So this is the pressure at a certain depth. All right. So this is, and this is also called absolute pressure. Absolute pressure, because it is the addition of all the pressures acting on the system. It is also the addition of the atmospheric pressure as well as the additional pressure caused due to the water. This was not caused due to water, but this is the result of the weight of the water that has increased the pressure and thus the absolute pressure as well. Absolute pressure. So this I think must be clear. And when I say that absolute pressure is equal to atmospheric pressure plus rho gh, then of course the rho gh term will be equal to the absolute pressure minus P naught. This is the same thing which has been given here. The difference in absolute pressure at a point and the atmospheric pressure must be equal to the rho gh term, where rho is the density of the fluid that you're talking about, g is the acceleration due to gravity, density, acceleration due to gravity, and h is the depth of the water. For example, if I have some vessel in the shape of this thing, I want to find the pressure at this point, then I will have to take this height. But if I have to take the pressure at this point, then the h will actually be this one. You have to take it from the top surface, whatever height or whatever depth it is. H more precisely represents the depth of the point. So this was it. And atmospheric pressure is defined is calculated, or it is estimated by a machine called barometer, in which there is this inverted glass tube and vacuum inside it, and when you place it in a tub of any liquid, what we use is the mercury Hg, so the readings are more easy to measure maybe. Okay, so in this case what we say is the mercury has risen 760 millimeter. That is why the atmospheric pressure is also sometimes called as 760 millimeter of mercury. But to be more precise in numbers, it is something of the order of 1.013 into 10 to the power 5 Pascal, where Pascal is the SI unit of pressure, force divided by area. So I think this is the part which has been given in your this is the same as 101.3 kilopascal. Anyway, it doesn't matter. Now coming to the part in which let's discuss the density first. It's very simple to understand. Density is defined as the mass of an object divided by the volume taken up by the object. It is as simple as that. In which it basically means if you have something an object or an object of 1 meter cube, how much mass does the object actually has? That will be called density. We also have something called relative density. Relative density, this is also represented by the form rho. Relative density is nothing but density of a particular object divided by density of water. All right, let me just quickly erase this thing. Yes, so this is something that I was talking about, that it is the density of the object divided by the density of the water, and this is taken at 4 degrees Celsius. Why? Because at 4 degrees Celsius the density of water is the maximum, because at lower or at higher temperatures the molecules have higher energy which will dissociate more and cause the fluid to expand. But while at the lower temperatures, maybe 3 degree and 2 degrees and 1 degree, the hydrogen bonds are not exactly in the same manner stacked together to give me the highest density. So that is why the density of water is highest at 4 degrees Celsius, and it is taken as 1000 kg per meter cube, and this will be the density of the object. So relative density, or this is also sometimes called specific gravity. You have to remember that it has nothing to do with the acceleration due to gravity or anything like that. It is more it is actually related to the density, and to be more precise, it is actually equal to the relative density of an object. So the density, I think, is covered in this mind map. Now coming to, I think we can discuss this part, Bernoulli's principle, because this is more of a surface tension which we will take it up later. Now when you have some system in which, let's say, there is this pipe in which there is this velocity v1 and velocity v2 of the stream flowing, and let's say this one has a height h with a ground h1, and this one has a height h2 with the ground v velocity and v2, right? So rho gh plus half rho v square plus just a second, plus the pressure at that point must be equal to P1 must be equal to whatever terms it was, rho gh2 plus half rho v2 square. I'm taking the same rho because it is the same fluid which is flowing, plus P2. This is called the Bernoulli's theorem, and it is very simple, because all you have to do is take the or I can even write it as a general equation that rho gh plus half rho v square plus p must be constant at any point inside the whole flow. So if you don't have the idea of the velocity, you can quickly estimate the pressure and the height, and you will have the value of velocity at that point. So this was about the Bernoulli's theorem. Where is it? Yeah, Bernoulli's principle. Now it has some. Let's talk about this one, equation of continuity. Yes. What equation of continuity basically says is, let's say you have this section was having area A1, this section was having area A2, the velocity of the stream was V1 here, the velocity of the stream was V2 here. Now let's say the water has moved till this point, this length in delta t time. Alright. In the same manner, it will also move to some certain lengths, right? L dash, and this is L in the same delta t. What I can say is the volume it has moved, the volume this area has moved must be equal to the volume which this must have moved, because the basic property of fluids is that it is incompressible in nature. So whatever you push, the other side will also get pushed in the same manner. So I can quickly find the volume of this one. V1 must be equal to V2 because the volume they have been displaced, and V1 can be said as yes, L and L dash. So V1 can be, this can be assumed as cylinder. So pi, or the area itself, A1 into L is equal to A2 into L dash. Now what is L here? L is nothing but the, can I say that L is nothing but the velocity V1 into delta time t? This velocity which has traveled to for a certain time which is delta t. So A1 into V1 delta t is equal to A2 into V2 delta t. Delta t gets cancelled out and you're left with A1 V1 is equal to A2 V2. This law is called the equation of continuity. Continuity means the stream is continuous in nature. The volume which get displaced on the left side must be equal to the volume which gets displaced on the right side itself. So this is called equation of continuity of continuity. All right. So this was the equation of continuity, and of course the Pascal law. There's something called Pascal's law. It is very basic in nature that let's say you're at a depth, at a depth h, then all the pressure will be exerting from equally from all sides. Or maybe I should make a point, because it will be more precise if it is a point and not having any physical dimensions. The point will have same pressure acting from all sides. That is the very basic nature of any fluid, how it exerts pressure. It is slightly different from solids. While in solids we can clearly see that this is the direction of force and this must be the direction of pressure, but inside a fluid pressure acts from all sides equally. So this is called Pascal's law. While yes, this part, venturimeter, I'll quickly tell you what is venturimeter here. Let's say there is this tank having water over this height h, and the area A1 of this face, and there's this hole which has been made on the basement, and if you make a hole, then water will come out of it, right? If the area of the hole A2, or the second hole is A2, then we can actually calculate the velocity of the stream, which is V is equal to under root 2gh divided by 1 minus A2 square divided by A1 square. This is the equation of E, or the velocity of efflux. Velocity of efflux of the stream. There is this one simplification that when A2 is actually very small as compared to A1, the maybe you have made a hole which is very small as compared to the whole area of the tank, then this can be assumed to be almost zero. Then the equation of efflux is equal to under root 2gh divided by 1 minus 0, so it remains as 2gh, and this is for very small orifice. Orifice means the hole on this point. So this was about the venturimeter. This can be derived, if you want to, this can be derived from the Bernoulli's equation. Or Bernoulli's principle. So I think this was clear, and this is a simplification. This velocity of efflux through a small orifice is a simplification that A1 is much lesser than A2. That's it. So I think this is also clear. Lift of an airway and spray of these all things are the results or the applications of Bernoulli's equation of, or Bernoulli's principle. Because when you have an aircraft, the velocity on the lower side of the wing is actually higher than the upper side of the wing. That is why it generates a lift, due to which it is able to fly. Now, there is something called viscosity, which I'll quickly go through it. That let's say there is this stream of water which is flowing, and you have something, a block of mass or maybe a sheet, which is flowing in that stream, and due to the stream, the movement, then in that case the stream itself should also exert some friction on it, right? Let's say you are rowing a boat, and the moment you stop rowing the boat will eventually come to rest very soon. Why? Because the water itself also exerts some this friction on it. So this F force with which you should move so that you are able to counter the friction is equal to minus eta into A into dv by dz or dh. What is this eta? Eta is called coefficient of viscosity. In many times it is simply said as viscosity of the thing. Now A is the area with which it has been in contact with the water. Area of contact. While dv by dh is the gradient of velocity. It means that, let's say you have some velocity here, the velocity on this side, all these velocities on different layers of the the flow need not be equal, and then it will raise to something called gradient. Why? Because it is in the this flow is in the contact of steady or static part of the pipe. Then its reduction, or then its velocity actually gets reduced, and we have, if you have a less velocity here and a higher velocity here, there is definitely going to be some sort of gradient, right? Gradient of velocity, rate at which velocity will increase when you go from the periphery to the radius of the pipe. Then this is called, or this equation will be applicable in that case. All right. I think yes. Where were we? Yes. This is something called Stokes law, in which if you have a sphere which is falling on inside a fluid, then the force of viscosity, the force of viscosity which actually acts on the system is actually 6 pi eta rv, 6 pi eta rv. All right. In this case as well, I think the mind map has missed something, that let's say you have this ball, metallic ball, going inside a fluid. Then after some depth, it actually achieves a terminal velocity. It is the final velocity, it is the maximum velocity which the ball can have. That terminal velocity is equal to 2 by 9 r square g divided by rho minus actually the density, sigma minus rho. Sigma is the density of the object minus the density of water divided by eta. I hope I have not missed any of the terms. This was missing in your mind map, so do remember this one as well. Now I think yes, this part is left. I'll quickly go through it. See, when you have a pipe in which the water is flowing, then there may be cases then that all these layers of water are flowing perfectly harmoniously with each other, making a very continuous sheet of water flowing. This sort of flow is called uh, an laminar flow, actually laminar flow. And if you have a flow in which the flows are not exactly, let's say the velocities are looking something like this, the water moves and then it bends after some point. This type of disuniformity, or the non-linear or non-harmonious movement of the water, is called turbulent flow. You must have seen this one uh, in reverse as well. Turbulent flow. This laminar flow, maybe you might have seen in chemistry labs, in which there is this hood for exhaust of gases, or exhaust of. So this was about the laminar flow, and there is this number. I think it is not given in the mind map. It is called Reynolds number. Reynolds number. It is given as rho rho r v, or sorry, rho vd. Yes, rho vd divided by eta, where rho is the density of water, v is the velocity at the middle point, and d is the diameter of the pipe, and eta is the viscosity of the pipe. When you have the Reynolds number within 1000, Reynolds number within 1000, this type of flow is called laminar flow. And if you have the Reynolds number maybe greater than 2000, it is called turbulent flow. Turbulent flow. So on these, on the basis of Reynolds number, it is decided whether it is a laminar flow or it is a turbulent flow. I think this part has been covered in much detail now. The only part which is left here is the surface tension. Surface tension is more of a theoretical thing. If you have the theory well with you, then you just have to remember a few formula and that will be it. The surface tension is actually directly proportional to the length of the interface. Interface means the point at which it is interacting but with two different mediums, for example air and the liquid. Then surface tension is the force with which it tries to pull the interface to make it to a minimum area. That surface tension is defined as F by L, or the force due to surface tension will actually be equal to S into L, nothing else. And the surface tension of course has some energy associated with it, due to which it is able to or it has the tendency to pull the object into its minimum area. So surface tension is actually dependent on area itself. So if you have the surface energy, that will be this thing. The capillary rise, it means that if you have a capillary, let's say there is this liquid filled tub in which you put a capillary, then due to surface tension the water actually rises up till a level, and this rise in the level h is given as the 2s cos theta into rho rg, right, where s is the surface tension. Cos theta is this angle, actually angle with which it touches the interface between the glass and the water and the air. So cos theta is the angle of interface, r is the radius of the capillary, rho is the density, and g is the acceleration due to gravity. Now we simply have something called, let me just show it here. Let's say you have this, maybe I can call it a drop of water, and maybe an air bubble. In this case, only this side is going to be an interface, right? Only the outside surface is going to be the interface. Interface means the meeting point of two different mediums. But in the air bubble is of course made up of liquid itself. Do not be fooled that it is made up of air or something. The layer of the, or the, what do you call it, this part this part of the bubble which you actually are able to see is nothing but fluid or the water itself. Then it clearly have two interface, right? This outer surface is also in an interface because it is in the presence of air, or in the it is between air and water, this surface, while the lower surface itself also is in contact with the water as well as the air. That is why it has two different interfaces. And the pressure, the excess pressure in this case is 2T upon R, where, what is this meaning of excess pressure? Excess pressure means if this P is the pressure in the environment, then the pressure inside the drop, P absolute, will be equal to P outside plus excess pressure. And the excess pressure inside the bubble, since it has two different interfaces which are both acting to reduce the surface area, then it will have twice the excess pressure. excess pressure is equal to 4T divided by R, where T is the surface tension, R is the radius of the drop or the radius of the air bubble in this equation. This is very, very important and very easy to remember as well. So please do remember this one. So this was about the surface tension, which was this particular box, 2s by R and 4s by R. Many times S is also represented in the form of T. So this can be said as 4T by R. T and S are both representation of the term which is surface tension. I hope this mind map was clear to you in the most crisp form as possible. So thank you.